I think I'll start now.
Sure. Yeah. Oh.
I mean, if anyone comes later, I will just admit. It's fine.
Yeah. Yeah. Okay. Fine.
So will you be here, or I mean, you don't?
So I'll be there. I'll admit the students. I'm also the co-host. So.
Yeah, that's fine. I mean, if you could be somewhere else, I'm also fine admitting all the others who come.
Yes. Yes.
Okay. So,
Okay.
All right. Hello, everyone. Can you everyone hear me?
Yes, sir.
Yes. So no. So it's a. So I'll start in a second. But just before I start, let me set some basic things. So it's not very easy taking a class over Zoom, because the whole interaction part is taken away. So I would like this session to be as much interactive as possible over this format. So if you do not have a great amount of background noise, you can unmute yourself, and if you have a stable internet connection and you are willing to, please also switch your video on. So it would be a great help to me, if I can see some of you, so that I can follow whether or not you are following me. So that would be a great help. Okay, so unless you have a high background noise, or your internet is unstable, I'll really appreciate if you can unmute yourself and answer my questions. And when I'm asking a question during the session, it would be very useful if you raise your hands and wait until I call on you before answering. So that would make things a bit more structured, because we have about close to 50 students. Otherwise, it can get a bit chaotic. Okay. Right. So let me try and share my screen. So does everyone see my screen?
Yes.
Yes, sir.
Okay, thank you. Yeah, so I had sent out a problem, so I'll discuss. Yes. So I'll discuss some problems in geometry and combinatorics. So let me go to full screen for a second. Yeah, and you people see the slides changing, right?
Yes, sir.
Okay, great, thanks. So, it's a short session of 1.5 hours, so we shall discuss some problems in geometry and combinatorics. So I have sent out a problem set, which I think you have received a few days earlier. So we have some geometry and combinatorics problems there. I don't think I'll get to discuss all of the problems in the set, so we'll see how much further we get. But don't worry, all the solutions will be shared with all the students, and the lecture, as I understand, will be available on YouTube. So even if you don't follow part of the lecture, it's nothing to worry. The lecture will be available later on YouTube, so you can come back to the lecture and rewatch again. Okay, so great. So let's start with the geometry portion of this session. So you guys have had lots of problem sessions over the last few days, I guess. So you have seen most of the things I'm going to talk about, I'm sure. But let me just briefly recall what are the basic geometry tools that we typically need to solve INMO level problems. So the first point is really very basic. Most of you have, most of you are very familiar with these things. Even at IMO level, you need to use these sort of things quite often. So these are just basics of configurations involving triangle and circles, like angle bisectors, medians, circumcircle, incircle, excircle associated with the triangle, and then tangents and secants, and power of a point, properties of cyclic quadrilaterals, properties of similar triangles, and things like that. So these are very basic things that we use very often. At the INMO level, there's some new things that are not strictly required, but might be useful if you have some understanding of. One of these things is some basic trigonometry. So for those of you who are in your +2, you have done much more of trigonometry in your curriculum itself. But for those of you who are probably standards 9 and 10, you might not be familiar with, depending on your state curriculum or which board you are studying. You might not have seen that much of trigonometry, but some basic ideas of trigonometry like sine rule, cosine rule, and how to apply these kind of things. This is sometimes useful. So typically INMO problems you don't need trigonometry to solve them, but sometimes if you can do some calculations using trigonometry, that might help you get at the solution. So that's one other thing I wanted to mention. And then the third point is probably the one that is one of the most interesting things that you get at this level. That's the problems involving collinearity and concurrence. So the main tools here, I'm sure all of you are familiar with, are Siva's theorem and Menela's theorem. So these are theorems that give necessary and sufficient conditions about 3 lines starting from a vertex of a triangle being concurrent and 3 points on the sides of a triangle being collinear. And then there is also this version of Siva's theorem, which is called the trigonometric form of Siva's theorem. That's also very useful often. And then there's this concept again. This is there will only be a very few problems at this level which will involve this concept of isogonal and isotomic conjugates, but it's again something that's useful to know and would definitely be very important as we progress from the INMO level to the IMO level. So that's this property that if you have 3 lines starting from 3 vertices of a triangle that are concurrent and you reflect the lines along the angle bisectors, then the reflected lines are also concurrent. So these are isogonal lines, and you prove it very easily using trigonometric form of Siva's theorem. So these pairs of points of concurrence, they are called isogonal conjugates. And similarly, you define isotomic conjugates where instead of reflecting the lines along the angle bisectors, you reflect the endpoint of the line which is on the opposite side of the triangle with respect to the midpoint of that side. So again, no. I'm not going to go through details of these configurations, but these are certain things that would be useful for you to be familiar with. So I understand that most of you are already familiar with this, but these are some things that you should keep in mind when we're trying to solve a problem. Okay, so that's about the basic tools, and we'll try to see some of these tools in action when we discuss some of the problems from the problem set. So let's start with problem 1. So this is a problem from the German National Olympiad from a couple of years ago, 2018. So let's just first read the problem, and then we'll try to think about the problem. So okay, for many of you who are more experienced in solving the problems, the solution sometimes comes naturally. Yes? Was there a question?
So no, I have solved this problem before from the problem.
Yeah, okay, so let me wait. Just wait for me to finish. So many of you, these are all competition problems. I'm not making these problems up, right? So many of you may have seen and solved these problems. But if you have solved this problem before, please wait and give others who might not have seen this problem before a chance to respond. Okay, please. All right. Yes. So let's read this problem. So we have a point in the interior of a triangle, and the rays joining that point to the. So let me maybe show the picture that's easier to understand. So P is a point in the interior of the triangle, and then I look at the lines AP, BP, and CP. They intersect the opposite sides at A1, B1, C1 respectively. And then you look at this construction, so you draw a perpendicular from A1 to B1, C1. The foot of the perpendicular is D. And then you are asked to show this equality. So this CD by BD is, you are required to show that CD by BD is equal to the product of the two ratios B1C by BC1 and C1A by AB1. Okay, so now, as I said, many of you might have already solved this problem. But if you have not seen the problem before, before I sent out the problem set or something like that, can any of you suggest when you first see the problem, how do you approach it? So that, see, from my point of view, what is more important is than just solving a specific problem. What is more important is to understand how to approach a new problem. Okay, so whenever we are encountering a new problem, it's very useful, in my opinion, to try to train our brain to think about it in a systematic way. Sometimes we just follow our natural instinct and do some construction, some calculation, and the problem is solved. But if we are always consciously thinking about why we are doing what we are doing, that kind of helps when we are given a new and hard problem. So if you are conscious about your own thought process, that is going to be very helpful when you encounter harder and harder problems. Okay, so let's try to think about it. How do we approach this problem? Okay, so anyone who has not solved this problem a long time ago, anyone who maybe just had seen this problem a couple of days ago and have had some idea about the problem, can you tell us how do you go about solving this problem?
This looks like Seva, so apply Seva maybe.
Yes, so this looks like Seva's theorem, particularly the right-hand side, right? The right-hand side looks like some terms, so missing from the Seva's theorem. So see, one observation that you should make immediately is that the point P is not special. There is no special property of the point P given in the problem. So P is an arbitrary point. So whatever the conclusion is, it is true for every P. So that immediately suggests to you that something generic should apply, something generic that's true for all interior points of a triangle, like Seva's theorem. So once you have thought about that, then you look at the right-hand side of what is given for you to prove, and then see that it's like Seva's theorem, except that you are missing the terms AC1 and no, not AC1. So you're missing the terms BA1 and A1C. Okay, so by Seva's theorem, the right-hand side, so it's again a very useful technique if you could work backwards. If you see a problem and immediately see how to proceed, that's great.
Hello, sir. Sir, I have some idea.
Yes.
Sir, if we show that A1C by BA1 is equal to CD by BD, then we will be done. So that is angle bisector theorem so if DA1 is the angle bisector of triangle BDC, if we show that, then we will be done.
Yes, that's exactly what is written here. You are exactly correct. So that's what I'm getting at, but let's take it a bit slow. So by Seva's theorem, we know that this equality, so we're going to work backwards, exactly what you said. We want to understand that what it has to be true for the conclusion to follow, right? So we are working backwards. We start with the right hand side, and immediately we simplify the right hand side to a single ratio, which is this CA1 by BA1. So the problem requires the reducers to show that CD by BD equal to CA1 by BA1, which is, as you point out, equivalent to showing that DA1 is the angle bisector of the angle BDC. Right? Okay, so now, those of you who have seen this type of configuration, this is a very common configuration. So for those of you who have seen this type of configuration, this property is something you know. But even if you haven't seen it before, we can quite easily see how to go about proving it. So we want to show that DA1 is bisector of angle BDC. Now, what information do we have about the point D? We have that angle A1DC1 is 90 degree. So if this is a bisector and we have a 90 degree line, a line making an angle 90 degree with the internal bisector, then the line DC1 must be the external bisector of the same angle, right? So how do we show? How do we show that a line is an internal bisector? A pair of lines which are making 90 degree angle with one another is the internal and external bisectors of an angle. And so this is a very standard configuration, and if you haven't seen it before, you should just try to prove it yourself. It's very easy using the angle bisector theorem. So what you do is you simply extend, so sorry, the figure is not complete here, but what we would do is we'd extend the line B1C1 so that it meets the line BC somewhere. Okay, it could be that they are parallel, but that case is degenerate, so that case can be handled very, very easily. Or if you are familiar with the concept of point at infinity, it can be handled using that. But let's not worry about that right now. So let's look at the non-degenerate case. So we have this this B1C1 extended meets the line BC at some point A2. Okay. So we know that if we could show that this CA1 by BA1, this ratio is same as CA2 by BA2, then that would imply, because this angle is 90 degree, that DA1 is the internal bisector of the angle BDC and DC1 is the external bisector of the angle BDC. Okay, so this is a very standard consequence of the angle bisector theorem. So if you have not seen it before, you should just try to prove it. It's a very easy thing to prove. Okay, so we have reduced our problem. So think what we have done so far. So we are working backwards from the start. And we have reduced our problem to showing simply an equality of ratios of CA1 by BA1 equal to CA2 by BA2, where A2 is the point where we intersect, this B1C1 intersects BC. Okay, so again, this is, I'm sure most of you have done this part of this problem sometime or the other. This is a single, a simple combination of Siva and Menelaus. So you apply Siva's theorem with respect to the point P, and you apply Menela's theorem with respect to the points A2, C1, D1. You write two ratios, both of which are equal to 1. You write down the equation that these two ratios are equal, most of the terms cancel, and you end up with this ratio. Okay, so this is, now I'm not going to write it out, but this is something you can do quite easily. Okay. All right, so let's take a few seconds to internalize this this thought process. And do you have any of you have questions? Everyone fine with the solution? Yeah, please, if you are not following, yes, Shashwat, please unmute yourself and ask a question.
So if B1 C1 turns out to be parallel to BC, then it would be a wrong case, no sir.
Sorry, again, if B1 C1 turns out to be parallel to BC, what will be the problem?
Then how come CA1 by BA1 will be CA2 by BA2?
Yes, so in that case, what will happen? So you can treat this case separately. So what will happen is that CA1 by BA1 will be equal to 1, and CA2. So you can think of it. So it will be formally true only if you look at only if you allow the ratios to be also infinite. So what will happen is that so A2 is the point on this line BC, right? So
Yes.
CA2 by BA2 can be 1 only if both of them are infinite. So in that case, one way to think about it is that if B1 C1 is parallel to BC, then they intersect at what is called the point at infinity. So in that case, CA1 will be equal to BA1, and CA2 and BA2 are both equal to infinity, and you can make sense. So it's not I don't want to get into details about this point at infinity thing, but you can make sense that the CA2 by BA2 is equal to 1 if A2 is taken to be the point at infinity. So you think about it as a point very far away on the line BC in the direction of B.
Okay,
and then so it's a, but if you're not familiar with this concept of point at infinity, you can simply treat this case separately. So if B1 C1 is parallel to BC, then what happens is that you already know that AC1 by C1B is equal to AB1 by B1C, right?
Yes, sir.
So that case, in that case, if you use that equality, things simplify a lot, and you can directly see that A1 has to be the midpoint of BC.
Okay, sir. Thank you.
Just by Siva's theorem, right? Because if B1 C1 is parallel, then A1 has to be the midpoint of BC. So that's not that's very easy to see just from Siva's theorem. So when you are a bit advanced, if you are doing this sort of problems for IMO, you will simply just say that this is equality, and if it's 1, then you are considering the point at infinity. But maybe at this stage, it's better, if you're not familiar with this point at infinity, it's just better to treat that case separately. If B1 C1 is parallel to BC, then it's easy by some other arguments. But if it is not, then you use this argument. Okay. All right. So everyone on board? Yeah, I don't see any more raised hands. Good. So shall we move on to the next problem?
Yes, sir.
Okay. Right. So this problem is from the USAMO from 2019. So let's read the problem, or at least let's look at the picture. So what we have here is we have a cyclic quadrilateral ABCD, and we have a condition on the side lengths which says that AD square plus BC square is equal to AB square. Okay, so it's not a very natural condition, but the condition is there. And then what we are doing is that we're picking a point on the line AB such that the angle APD is equal to the angle BPC. And then we're joining P to the intersection of the diagonals, which we call E, and extend so that it meets CD at some point N. And we are supposed to show that this point N bisects the line CD. My figures are not accurate at all, as you can see that N is nowhere near being the midpoint of CD, but don't worry about that now. So we have to show that this line P bisects the line segment CD. Okay, so the same deal again. How do you go about it? This question again is meant for people who have only recently seen this problem and not have solved this a long time ago. So yes.
So can you show the problem statement once?
Yes. Do you want to see the statement? Yes.
Okay, sir, done.
Good. Okay, so I find it more useful to look at the figure. Yes. So any ideas on how we should go about solving this problem? How we should think about approaching this problem? Has any of you solved this problem? Have any of you solved this problem? Have any of you seen this problem before?
Sir, what do you have to do? What we have to prove here?
Sorry, I can't hear you very well. Can you speak a bit louder?
Sir, what we have to prove here?
Oh, we have to prove that this line PE, when I extend that it intersects CD at N, what I have to prove is that N is the midpoint of CD.
We can try to prove that EN is the median.
Yeah, EN is the median, sure. But how do you translate it to something more manageable? Okay, so someone has seen this problem before. Kazi Aryan, can you have you solved this problem, Kazi?
Yeah.
Okay, so don't tell us how you solved this problem, but can you share some insight
Sure.
on how you approach this problem?
Sure. Like the condition looks like kind of excuse me, Pythagoras' theorem, but it's like written kind of differently. So that like kind of motivates us to like add in circles at A and B, which intersect at like say points P and Q, such that P is taken. Uh, so that like helps us in understanding D and C to some extent.
Can you repeat once more what you said? So I understand. So you are saying that there is a Pythagorean triple. So AD, BC,
So
AB, they form a Pythagorean triple. But how are you going to use that?
Like it looks like Pythagoras' theorem. So uh, just a second, I'll like check my solution once again. Uh, Uh, okay, yeah. So like, um, so we could like first try to understand P, right? Like how P fits into the diagram, and like
Yes,
also there's
that's a great
a,
point. Yes.
condition kind of is like kind of Pythagorean like. So like what we can do is like we can uh, try to construct a semicircle kind of thing with like AB, like not
Mm-hmm.
exactly a semicircle, sorry, like a circle with radius with center A and radius AD and center B and radius BC.
Mm-hmm.
So where they intersect, then you'd get something like uh, uh, just a second. Yeah, so like from there, if we like draw a good enough diagram, then we can like notice something like P would lie on X and Y, when X and Y are the two circle like intersection points of the circle. And
Okay. So
from
you
there,
make a
it
very good
kind of
point that
becomes
you want to draw some precise diagram to notice some properties of the configuration. That's actually a very good technique. Most of the time, if you have like proper compass and drawing equipment, sometimes just drawing the figure exactly according to what is given in the problem can be very useful.
so like we can
So,
do this
okay, so
like
this is this is one approach, but actually I want to discuss a different approach. So let me maybe go on discussing a slightly different approach. So of course, the basic idea is the same. So you have to interpret this point P in light of the given condition. So I had a couple of raised hands. So Shashwat and who else I forget. Um, Jyotishman, yes. So Jyotishman, maybe you want to go first.
Yeah, I just thought of like we can use the similarity of ADP and PCB like in the relation of the sides to establish the length and all, like a relation between them.
Okay, that's a very great idea, and that's what I will. The solution I want to discuss exactly goes along that line. So we'll come back to it later. Shashwat, you
Yes, the
want to
same
first?
approach. I was also thinking about similarity.
Oh, great. Yes, so that's the approach we are going to discuss. And then there's a question in the chat: is it good to use complex? You can, but I don't necessarily think that it will make it any simpler. So if you are very good with your complex numbers or even coordinate geometry here, one can probably get a solution. But I expect that the calculations are not going. This does not to me seem a problem which is particularly suited to complex numbers. But I mean, you can try. But so let's try the similarity approach. Okay, so
I was thinking of inverting.
yes, but okay, so see, there are many advanced things that you can do, but see, inversion is not even required at IMO level. Okay, so let us try to keep ourselves on more elementary grounds. Okay, so right. Sorry, just a second. Yes. So what I want to do is just I want to again work backwards. It's a favorite thing as you must have surmised by now. I want to work backwards. So what has to happen if En has to be the median of the triangle EDC? So notice that this triangle EDC and this triangle EAB, they're similar. It's a basic property of cyclic quadrilaterals, right? So if En is the median of the triangle EDC, and if Em then is the median of the triangle EAB, then what must be true is that the angle, the triangle AEM and the triangle DEN, they must be similar. right?
So can you repeat which two triangles?
Oh, so the triangle EDN, this triangle, EDN, this triangle, and the triangle EAM. M is the midpoint of AB. Now, if you have two similar triangles and then you draw medians on both of them starting from the similar vertices, then the triangle you get where median is one of the sides, those are similar. It's just calculating ratios. Okay, so now that means angle AEM, this angle, I probably should have drawn the line EM, but you can see. So the angle AEM, that, yes. So maybe, yes, maybe just look at this page. So the angle CEN, okay, I have, okay, so I've done it the other way. So the triangles CEN and the triangles BEM must also be similar. So that would mean that the angle CEN must be equal to the angle AEP. So this is just by opposite angles. But the angle AEP then must also be equal to the angle BEM. This is by similarity. So CEN and BEM, they have to be equal by similarity. And CEN and AEP are opposite angles, so they must be equal. So what we get is that angle AEP and angle BEM must be similar. So that means that the line EM and the line EP, they're isogonal lines. So what it means is that the line EP must be the reflection of the median, which is the line EM, along the internal bisectors. Okay, so as most of you would know, then it would mean that what we are required to show really is that the line EP is a symmedian in the triangle AEB. Okay. So for those of you who might not have
What is median?
Yeah, what is the median? I was coming to that. So median is reflection of a median into the angle bisector. So if you reflect the median of a triangle on the angle bisector, that is called the symmedian. Okay, so it's just a name. But what is really useful for us is this property that if you have symmedian, so if EP is the symmedian of triangle AEB, then the point P is characterized by AP by BP. So this ratio is actually the square of the ratios of the corresponding sides. So AP by BP is EA square by EB square. Okay.
Yes, sir.
Fine. So now again, we are in a cyclic quadrilateral, so no need to stop here. So EA by EB, we know. So remember, we have to use some condition about AD and BC. So whenever I see this EA by EB ratio, I should immediately think about the similar triangles AED and BEC, which gives me that EA by EB is equal to AD by BC. So EA square by EB square is equal to AD square by BC square. So I have now reduced the whole problem into showing that AP by BP is equal to AD square by BC square. Now that I see the given condition, AB square equal to AD square by BC square, it seems much more natural. Okay, so what we really have to show is the following. Suppose I take a point, so remember that the point P was given to us using some angle condition, right? And now we have reduced the problem into showing some ratio condition. So what is it we really try to show here is that we take a point P prime on the side AB such that AP prime by BP prime is this. Now such a point P is unique, right? So all we have to show is that this point P prime satisfies the angle condition given in the definition of P. So that would show that P prime and P are the same points, which is what we are after. Okay, so we just take a point P prime on this side, which satisfies this ratio equality. And then we'll have to show that angle A. So really, I have not shown a P prime in the picture, but P prime is really P. But instead of defining the way it is defined in the statement of the problem, I defined it by this ratio. And what I have to show is that angle AP prime M is equal to angle angle AP prime D is equal to angle BP prime C. But now, this AD square plus BC square equal to AB square, together with this ratio assumption, immediately tells us that AP prime times AB is AD square and BP prime times BA is BC square. Right? Because the sum of these two, sum of AP prime times AB plus BP prime times BA is equal to AB square. So P prime exactly is the point which divides this AB square into the ratio AD square plus BC square. Now this is a very common configuration, right? So we have lots of similarity. We have this AP prime D, which is similar to ABD, and we have BP prime C that is similar to BCA. Okay, so then you just do some amount of angle change using the similarity. So you say that AP prime D is equal to ADB by similarity. Then you use the property of cyclic quadrilateral to show that that is equal to ACB. Then you use similarity again to show that it's equal to BP prime C. So what we get is that angle AP prime D is equal to angle BP prime C. But such a point P prime is unique, and our point P was defined exactly using this condition. So this tells us that P prime is equal to P, which is exactly what we were after. Okay. Right. So again, so what did we do here? So again, we used a lot of back calculation to reduce the problem into a reasonably, we reduced the problem into the one which sort of seems natural rather than the way the problem is phrased. It's quite unnatural. And then one extra thing we had to use is the property of a symmetrian. So that's why, one of the things I said, that's properties of this isogonal lines and isogonal conjugates, that's something useful to know. And then we had to use a lot of properties of similar triangles. So it's not, if you think about it, it's not a very difficult problem, but the challenge here is to somehow understand how to use the given condition AD square plus BC square equal to AB square. So what Kazi you were saying before is that you use that to form some right angle triangle and deduce some information from that. So that's a different approach. And presumably that also works. But this is also another approach. So you kind of use the fact AD square plus BC square equal to AB square to understand that P is a special point which divides the line AB into exactly that squares of those ratios, so that you have this AP times AB equal to AD square and BP times BA equal to BC square, which gives rise to lots of similar triangles. So you can just start with that guess and move ahead. That also works perfectly fine. But if you work backwards a little bit, then that gives you confidence that exactly that must happen. So that's a good way to go about solving this problem. Okay, any questions about this problem? All right. Okay. So let's move on to problem 3. So this is another USMO problem. Yeah, this actually, yeah, again, it's not that difficult, but it's a bit complicated because lots of things are going on. So let's read the problem. So we have a triangle with an orthocenter, and then we look at the orthocenter is H, and P is the second intersection of the triangle A, the circumcircle of the triangle AHC with the internal bisector of the angle A. Okay, so let's look at the picture.
Can you please show the question once again?
Yes, please. Just give me a second. Okay, so I'll give you a minute to read, and then I'll move on to the picture.
Okay, you can move on.
Okay, great. Yes, so again, this one actually is suited to using complex analysis because the orthocenter has some nice expression in terms of, so if you replace the, if you write the vertices of the triangle in complex coordinates, it's, the orthocenter is can be expressed in a nice way. But again, you don't have to do complex analysis. It's still a lot of calculation. It's much easier to this is at the core of it. This is an angle chasing problem. The problem is stated in a way to purposefully misdirect you. So lots of points, lots of line, lots of things going on. But if you kind of can unveil the core of the problem, you'll see that it's an angle chasing problem. Okay, so
can we get like 5 minutes to try?
See, I mean, I have very limited time, right? So if one of the reasons I sent this problem set ahead in advance is because I wanted to give you a chance to try, but really we cannot have 5 minutes here to try. So let's give some of the people who might have tried this problem already a chance. So, but let's go through the picture before that. So we have this triangle ABC. H is the orthocenter. Look at the circumcircle of the triangle AHC, which intersects the angle bisector AP at the point P. Then what do? We look at the circumcenter of the triangle APB. So we look at this triangle APB, and X is the circumcenter. Okay, so and then Y is the orthocenter of the triangle APC. So I have this triangle APC, Y is its orthocenter. What we have to show is that XY is equal to the circumradius of the triangle ABC. Okay, yes, so anyone who has any idea about how to do it in a synthetic way, so I mean, someone has already said complex. You can presumably try coordinate geometry or trigonometry also, because there are lots of angles here. But anyone has any idea on how to approach this in a synthetic way? So one of the difficulties with this problem is that it's not immediately clear how to work backwards. XY is equal to R. That's not a lot to go on. It is something, but it's still not a lot. I mean, you have to make some observation. Yes.
I think we can somehow prove that BC is perpendicular to XY with spiral symmetry.
So what do you want to show? You want to show BC is perpendicular to XY?
That's my
Possible.
process.
Yeah, is that true? I'm not sure it's possible, but yeah, and why would that help? Suppose you,
No, it's just some progress.
yeah, okay, of course, it's a progress. So, yes. Okay, so let's,
Yes, then we can send bx to at p somehow.
uh, what do you mean you send bx at p?
Uh, like bx to my with spiral symmetry.
I am not following you. So we want to somehow calculate the length of xy, right? So I understand if you can prove that xy is perpendicular to BC, that is something, but how? I'm not sure how you exactly proceed from there. Yeah, so I mean, I'm not sure. So this is not the way I did the problem, but there are many possible approaches. Um, so it could very well be an alternative approach, but let me try to explain how I went about solving the problem. So as I said, it's not immediate without any information, any further information on the configuration, how to work backwards. So in such a situation, what I like to do is I want to get as much information about the configuration as possible, and then see whether any of those helps me make a guess about what needs to be proved. Okay, so there are two observations I want to make here. Now these are all basic observations. So if you have not, these will be familiar to almost all of you. But if you haven't, you should just take these properties as exercises. So the first property is that if you look at the triangle AHC, its circumcenter, of course, it lies on the perpendicular bisector of AC, but not only that, the circumcenter actually is the reflection of O prime on AC, where O prime is the circumcenter of ABC. Okay, that's a very easy angle chasing problem. So you just have to show that the angle AO prime is equal to angle AO prime. That's all is needed. I mean, since you know that angle AHC is equal to 180 degree minus angle B, that's quite obvious. Okay, so that's the first observation I wanted to make. And the second observation I wanted to make is that, see, angle Y is the orthocenter of triangle APC. Now that means the angle AYC is equal to 180 degree minus angle APC. But angle APC is the same as angle AHC because they are concyclic. And angle AHC is 180 degree minus angle B. So what it means is that angle AYC is the same as angle ABC. So that means that Y also lies on the circumcenter of ABC. Okay. No, so these are easy observations. So good practice sometimes solving these problems is that whenever you are given a configuration, you sort of jot down what are the immediate consequences of the given configurations that you can find. So here we have listed two. I mean, there are many more, but these two are the most relevant to the problem. So I have singled them out. Now, with this information, what would be your guess? How do we go about showing that xy is equal to r? So one immediate observation is that if xy has to be equal to r, then xy equal to O prime y. right? So because y is on the circumcircle and O prime is the center, so O prime y is equal to r, xy equal to r. So this is an isosceles triangle here. Of course, we don't know that, but we have to prove that. And if xy has to be equal to r, then this triangle O prime xy will be isosceles. But there is another isosceles triangle with equal side lengths r here, right? So O prime OA, that's also an isosceles triangle with the equal sides being equal to r. So one possible guess, so this is a guess yet, right? So this is not like the previous problems where we are working from backwards, in concrete steps. So here
Sir,
it says again. Yes, go ahead.
can we show that OA O prime is congruent to O prime XY?
Yes, that's exactly what we guess that will be. So that definitely is sufficient to prove. So if we can prove that O prime A is congruent with O prime XY, then definitely we are done. I'm not sure at this point that that is the right way to go, but that is the most natural guess to make. That's the point I want to make. Okay. So exactly here it is here what we have written here is that it suffices to show that the triangle O prime XY is congruent to triangle O prime OA. Now what does that mean? So I have to show equality of two sides, equality of one side and one angle, right? So I have to show that O prime O prime is equal to X O prime, but that again reduces to inequality of angles, right? Because then O prime XO is an isosceles triangle. So if I can show O prime XO is equal to O prime OX, that implies O prime O is equal to O prime X. So this is an equality of angle, O prime OX equal to O prime XO. And then I also have to show that Y O prime X, this angle, is equal to A O prime O. So if I can show Y O prime X equal to A O prime O and O prime O equal to O prime X, then I'll be done. Okay, so this Y O prime X equal to A O prime O, that is same as showing X O prime O is equal to A O prime Y. I've just added the common angle. So this is why I was saying that this is an angle chasing problem, because once you have made the correct guesses, you reduce the whole problem into showing these two equalities of angles. So this O prime OX equal to O prime XO and X O prime O equal to A O prime Y. Now, once you have come to this conclusion, it's actually quite easy. This is an angle chase. Both these angles, all of these angles can actually be chased in terms of the angles of the triangle ABC. So I actually don't want to go through the angle chase part. It's quite standard. So you can just try doing it yourself. If you get stuck, of course, the solution will be provided. So don't worry about that. But the main point I wanted to make is that the trick here was to the configuration given is quite complicated and cumbersome. So somehow the trick is to identify the key elements and reduce it to a problem about showing equalities of angles that we understand better. So once we actually could reduce it to these equalities of these two pairs of angles, then the problem becomes fairly standard, not difficult at all. But the challenge is to see through this complicated configurations and arrive at this equalities of angles. Okay, any questions? All right. Okay. So there are no more questions. Let's move on. As time is quite flying, so I have less than half an hour left. So what I will do is that I will discuss some combinatorics problems. So there is one geometry problem left, which I'll provide a solution, but let's not try and discuss this now. Let's do a little bit of combinatorics in what time is left. Okay, so again, just start with a list of basic tools and techniques that will be useful for you at the INMO level combinatorics. So the first thing is obvious, right? I mean, this is you need this even at RMO level, just the basic knowledge of permutation and combination. And then these techniques of generating functions and recurrence relations. So how to solve recurrence relations using generating functions and how to do lots of different countings using generating functions. That's something that comes in quite handy sometimes. And then the other thing that is extremely useful is the pigeonhole principle. If you put like k plus 1 things in k boxes, at least one box must contain 2 things. That's thing. And then this is something that is, I don't know how familiar, I mean, I'm sure some of you are familiar with it, but I'm not sure if all of you are familiar with the basic terminologies of graph theory. So, this is, so you have vertices and edges. So you have a number of vertices and some pairs of them are connected to edges. So lots of combinatorics problems can be translated into in a very nice way in terms of graphs. So that's something that's going to be some type of combinatorics problems are very easily accessible if you think in terms of graphs. That's something useful. And then a little bit of Ramsey theory sometimes helps. So what is Ramsey theory? If you have never heard this word before, all of you have seen this theorem, right? If you have 6 people at a party, then there always exists 3 such that they're mutual friends, or 3 such that they're mutual strangers, right? So that's a so if you change 6 and 3 by some numbers n and sufficiently large number, which is called Rnn, the Ramsey number, so the result is still true. So given any number n, you can find a large party with large numbers, large number of people, such that there are at least n people who are mutually friends, or at least n people who are mutually strangers. So these types of problems are called problems of Ramsey theory. So the basic argument, how using pigeonhole principle, how you show these kind of things, it comes in useful for certain problems. And then there is this very useful thing which is called counting in 2 ways. So you have the same quantity and then you try to count it in 2 ways, and then you equate the 2 things and you arrive at some conclusion. That's the general hypothesis. That's the general idea of this technique, which is extremely useful. So these are some of the basic techniques to keep in mind when you are attacking a combinatorics problem at this level. So right. So let's start with problem 5. Okay, so this is a quite classical problem actually. So this is something called Lubel-Yamamoto-Morel inequality. So what is the problem? The problem is saying that you have a set of n elements, and you have a number of subsets such that the subsets are not contained in one another. So there does not exist. So you have a family of subsets such that no 2 of them are such that one is contained in the other. So of course, you cannot have too many subsets of this kind, right? Because if you had, for example, all subsets, then of course some will contain the others. So what the result gives is that some kind of upper bound of the size of this family. So if AK is the number of subsets in this family of size k, then you are required to prove that the summation k equal to 0 to n ak by n choose k is less than equal to 1. Okay, so did anyone have a chance to try this problem? Someone has seen this before? No one? Okay, yeah. So there are lots of solutions of this, lots of ways to solve this problem. But the one I like most is the one that is done by counting in 2 ways. So let's just rewrite the inequality, right? So let's choose let's expand out this n choose k, the combination coefficient. So I write n choose k as n factorial by k factorial times n minus k factorial. So then that reduces the problem to showing this summation ak times k factorial times n minus k factorial is upper bounded by n factorial. Okay, so now remember that U is a set of n elements. So the right hand side has a ready-made combinatorial interpretation, right? So it's the set of size of all permutations of U. Okay. So if we could show that there exist these many, the left hand side many distinct permutations of a set of size n, then we'll be done, right? Because the total number of permutations is n factorial. So if we could show that there are at least these many distinct permutations, then of course that number has to be less than n factorial. Okay. So how do we construct? So the problem is reduces to constructing these many permutations. So what is a natural way to so given a set, so suppose I take an element of this family script A, I fix a set S with k elements. So how do I, what is the natural way to construct a permutation associated with this set?
Sir, take all the elements in S and then permute them and permute the remaining somewhere else.
Yes, exactly. So that's the most natural way to do it. So you take S and you send S to 1 to k in some order and permute the other elements to k plus 1 up to n. So how many such permutations are there?
AK into k factorial and n minus k factorial.
Exactly. So you have, for a fixed S, you can just permute the elements of S within 1 to k in a k factorial ways. You can permute the rest in n minus k factorial ways. And then you have ak many elements of S, right? So the total number of permutations you get by this way is exactly our left hand side. So what is left to show? So remember, we have so far not used the condition on the family of subsets, right? So we are not done yet. So what we have to show is that all these permutations are distinct. So that is something we haven't shown yet, right? But once you have this construction, that's actually very easy. So suppose you end up with the same permutation coming from two different S1 and S2. So there is a permutation which you get starting from S1 as well as you get starting from S2. And suppose S1 is smaller than S2. But then because of the definition that S1 sends the elements of S1 to 1 to, so say S1 is K1 and size of S1 is K1 and size of S2 is K2. So S1 sends S1 is sent to 1 to K1 and S2 is sent to 1 to K2. Since K2 is bigger than equal to K1, that will imply that S1 actually is contained in S2, which is exactly what is precluded by the hypothesis of the theorem. So the hypothesis on the family A ensures that all the permutations I generate this way is they are all different. So these are all distinct permutations, and hence their total number is upper bounded by the total number of permutations, which is n factorial. Okay, that's it's not so once you get the right idea, it's actually not hard. It's actually quite easy. But that's pretty much true for all combinatorics problems. Okay, any question?
How did you find the number of permutations?
How did I find the number of permutations satisfying what?
In the second point, you wrote the number of permutations.
Here you mean this equation? You mean this one?
Yes, sir.
So okay. So I have fixed the set A, and I am considering all permutations that sends elements of S to 1 to K. Okay. So how do I do that? So I can assign all elements. So there are K elements of S, and I can assign them to 1 to K in any manner I like. Right? So that is K factorial. And then the remaining n minus K elements I can assign to K plus 1 to n again in any manner I like. So that's another n minus K factorial. So the total number of permutations I get for a fixed S is K factorial times n minus K. Now there are ak many S of size K. So that gives me ak times K factorial times n minus K factorial coming from sets of size K. And now I sum over all possible values of K. So that gives me all possible permutations I can get starting with sets S in the family. Okay. Alright, any other questions? Alright, so okay. Let's then move on to problem 6. See, problem 6 is a repeated example of how combinatorics problems, easy combinatorics problems can seem hard. The problem is stated in such a cumbersome way that you might just get intimidated by looking at the size of the problem. So let's read the problem. So we have lots of storytelling, which is not essential to the problem, but let's go ahead. So there's a tribe of several families which are always fighting, and they're not going to shake hands. And you cannot have 4 or more of them in a circle such that they're willing to shake hands with the next people. And then there is some sort of a mediator who collects 3 coins from each family and then gives back 2 to every pair who is willing to shake hands. And then you have to show that somehow this mediator guy makes some money. Okay, so it's a some sort of cumbersome story. But the point I try to make is that if you translate into right language, this problem actually becomes very easy. So in this case, it turns out to be really the right language to translate this problem is the language of graph theory. Okay, so how do you make a graph out of this problem? So each family is a vertex in the graph. So let's suppose that there are n families, and then I add an edge between the 2 families only if they're willing to shake hands. Okay, so now how many gold this guy collects? For each family, he gets 3 pieces of gold, right? So he's collecting 3n many pieces of gold. And how many pieces is he paying back? For each handshake, he's paying back 2. The number of handshakes is exactly the number of edges in the graph. So he's paying out 2 many coins. And the given condition that you cannot assemble 4 or more chiefs in a circle so that everyone is willing to shake their neighbor's hands, that means that in the graph you cannot find a cycle of length 4 or 5. So a cycle means a closed path. So you start at a vertex and then you traverse along it and you come back to the same vertex.
Yes, sir.
Yes.
Sir,
Go
could you
ahead.
please explain me the last line of the problem, that is the question?
Oh, this one, we show that the number of pieces of gold collected by the druid exceeds the number of pieces paid out by at least 3.
That paid
This
out by
one?
at least 3.
Yes, so this is exactly this. So 2E is the amount of gold he pays out, and 3N is the amount he collects. So what we have to show is that 3N is at least 2E plus 3. That's what it means.
Okay.
Right. So all this big one-page problem really translates to this one-line problem, is that you have a graph with n vertices and e edges, such that it has no cycles of length 4 or more, and you have to show 2e is less than or equal to 3n minus 3. That's all there is. Okay, so if you can do this translation, this problem actually is very easy. Okay, so I'll go through it quite quickly, because if you are familiar with basics of graph, it is not very difficult. You can just go through it. After the translation, you can just do the problem when you want. But let's just quickly go through this. So what you do is typically, you consider a spanning tree. Spanning tree means that you take a graph, a subgraph, so you delete some of the edges, such that you still connect to each of the vertex, but you do not have any cycle. So the resulting graph is a tree, which means that in the graph there is no cycle. So in a graph of size n, a spanning tree always has only n minus 1 edges. Now what we will do is that after we have had the spanning tree, we will add back the deleted edges one by one. Because it's a spanning tree, whenever you add a new edge, at least one cycle will be created. And because of the condition, that cycle always has to be a triangle, because there are no cycles of length 4 or more. So whenever you add, so you start with the spanning tree and you keep adding edges one by one, the edges you deleted to get to the spanning tree. Then you keep creating one new triangle at each time. And it's easy to see, it's very easy to see by drawing a picture, that whenever you add one edge, the triangle that is created, the other two sides of this triangle must be the sides of the spanning tree itself. Otherwise, you are going to create a 4 cycle. So it means that the number of vertices you are going to add, the number of edges that you are going to add is going to be upper bounded by the number of edges in the spanning tree by 2. So that gives you E is upper bounded by n minus 1 plus n minus 1 by 2, which is exactly what we get here. Okay, so that's this graph theory bit is actually quite easy. So I went through it quite fast, but you can just think through this yourself. But the point is that it was crucial to just translate it into the right language. All right. Any questions? Any questions about this problem?
Sir, could you repeat how we got the upper bound on the number of edges?
Yes. So okay. So we start with this spanning tree, right? So that is n minus 1, and then we keep adding one edge, one of the deleted edges one by one, right? Now
Yes,
what
sir.
I'm saying is that each deleted edge connects to two of the edges of the spanning tree to form a triangle. So each time I add one new edge, I spend two of the edges of the spanning tree, and these edges cannot be reused. So if you are going to reuse one of these edges for a later triangle, you will see that you will create a 4 cycle. That's actually very easy to check. You can just draw some diagram and check it. So that means the number of extra edges I'm going to add, each of them costs me at least 2 edges of the original spanning tree. So if I'm going to add more than n by 1, n minus 1 by too many edges, then I'm going to spend all the edges of my spanning tree. So I cannot do that. I mean, more than the edges I have in my spanning tree. We cannot do that. So the number of edges I can add is upper bounded by half the number of edges in the spanning tree. So that's how we get this n minus 1 plus n minus 1 by 2. Okay.
Yes, sir.
All right. Okay. So yeah. So you don't see any more raised hands. So let's quickly. I think probably we just have barely time to do another problem. So this is from INMOTC 2002. It's again a very common type of problem. So it's good to have some experience with this type of problem. So what does it say? It says that there are 200 students participating in a math contest, and there are 6 problems to solve. And what is given is that each problem has been solved by at least 120 people. And what we have to prove is that there must be 2 participants such that every problem, so if you look at these 2 participants together, they have solved all the problems. Okay, so at least one of them have solved all the problems. Now, for those of you who are familiar with what is called probabilistic methods, this is an extremely easy problem to solve. But I'm not going to assume that you have seen probabilistic methods before, so I'll give a different solution. But if you are, if you want to ask me how I thought of this solution, then the answer will be because I solved it by probabilistic method before. But it's so I don't have a very good intuition of how would I go about thinking about this problem if I did not know of this probabilistic method. But I want to illustrate a useful concept which is called the incidence matrix, which you will find will be useful in lots of other instances. So what is an incidence matrix? An incidence matrix is a matrix that will encode all the information in this problem. So here we'll have a 200 by 6 matrix. Each row will correspond to a student and each column will correspond to a problem. And then I'll set the ijth entry to be equal to 1 if the student I has solved the problem j. Otherwise, I'll set it to 0. So this matrix encodes all the problems, all the information that is there in the problem. Okay. And what do I have to show? I have to show that if I can find 2 rows of this matrix such that if I say sum the 2 rows, each element is at least 1. There is no 0 in the sum of those 2 rows. So that's exactly the translation of the statement of the problem. So now the following quantity is actually, if you think about it, the following quantity is quite natural to define in the context of this problem. So let n denote the number of pairs ij, i prime j, such that neither I nor I prime has solved the problem j, which means mij, comma m prime ij is equal to 0, 0. So what we will do is that we will count this number n in 2 different ways. Now, in each column, there are at most 80 zeros, right? Because each problem has been solved by at least 120 people. So counting by column, n is upper bounded by number of problems, which is 6, times 80 choose 2. So for each j, there are at most 80 choose 2 such pairs. So n is upper bounded by 6 times 80 choose 2, which you can calculate and see that it is 18,960. And suppose the claim that we were required to prove is false. So suppose that there are pairs of students, each pair of students, for each pair of students, there is some problem J that they did not solve among themselves. So that means each pair of students contributes at least 1 to the sum n. So that would mean that n is at least 200 choose 2, which again you can calculate and see that 19,900. So by counting in one way, we got n is upper bounded by 18,960, and counting in another way, assuming the conclusion of the problem is false, we got n is bigger than or equal to 19,900. So our assumption that the conclusion of the problem is false must be wrong, because we have arrived at a contradiction. So there must be a pair of students, at least there must be actually 900 pairs of students who have solved the problem, who have solved all pairs of problems among themselves. Okay, so that's the solution of this problem. We are really out of time, but maybe I can take, if you have a couple of quick questions, I can answer them.
So where will we get the solutions?
Yes, so I will send it to HBCSE and then they will share with you. So don't worry about it. I'll send it either later tonight or tomorrow, but you will get it soon.
Sir, could you please tell what variable we will have to consider if we want to solve by probabilistic method this problem?
Oh, in this problem, you just pick 2 students randomly, and you calculate the probability that these randomly chosen pair of students have not solved all the problems among themselves, and you show that the probability of that event is strictly less than 1. So that means with positive probability, the students have solved all the problems among themselves, which means that there must exist a pair of students who have solved all the problems among themselves. Okay, so I mean, for those of you who have never seen any probabilistic argument before, it did not make any sense. Don't worry, I'll include a basic sketch of this probabilistic solution in the solution set that I sent. Okay, I think I'm out of time. Yes. Last question.
There is a counter example for problem 8.
Problem 8, is there a counter example? Okay, so can you, oh really? Okay, so what is the counter example?
Sir, problem 8, not 6.
Yeah, 8, yeah, tell me. So this is the thing where you can delete one of the elements.
Yes,
divide.
sir, take 1, 5 and 6 ones. Or take 1, 3 and 4 ones.
1, 3 and 4 ones.
Yes.
And how are you going to, if you delete one of the ones, what is going to happen? Then you are left with 1, 3 and 3 ones.
Yes. So it is trivial.
You have to divide them into equal size, right? The problem states that you have to divide them into equal size. So there are 2n plus 1 many elements. You delete one, and the remaining 2n has to be divided equally. So there has to be n elements on each side, such that their sum is 1. Is that not how I've stated the problem? Maybe I have typed it wrong. So the problem statement, okay, so just I'll take 1 minute. If I have typed it incorrectly, I'll correct it when sending in the solution. But the problem statement is you have 2n plus 1 many positive integers. You take out any of those, the remaining 2n numbers can be divided into 2 groups of size n each, such that the sum of those 2 groups of size n each are equal. This equal size partition is important. If I have not mentioned it in the problem set, then I have typed it wrong. I'll correct it and send it. Okay. Does that answer your question? So your counter example will not be valid if I add that condition, if I have not added it already. Okay. Yeah. So I'll check once before sending the solutions. All right. Okay, yeah, thanks for attending the lecture and good luck with your INMO. All right, okay, so I'll.
Thank you, sir.
Thank you. Thank you,
Thank you,
Dr.
sir.
Basu. Thank you.
Thank you, sir.
Yeah, okay, I will,
Thank
move
you,
on.
sir.
Thank you. Sumana
Yeah.
madam, so I'll just
Yeah.
and
Yeah, you can leave. Yeah, we'll end the meeting. Yes. Yes.
okay, thank you.
Yeah, Ashish?